Hello guys, welcome to another episode of this tutorial. Just like I said in the last video, we'll be looking at the constant pressure process, that is the isobaric process. So just like in the other video, we treated the no-flow process. We started with the constant pressure process. We solved some examples and also explained some things here. So in this video, we'll be looking at the constant pressure process. So what is a constant pressure process? It's a process whereby the value of the pressure is kept constant or pressure remains the same throughout the process. So from the first law, let's say mathematically, we have that dq plus dw is equal to du. So from our knowledge of differentiation, we have, but remember that work done, which is w, is equal to pv. So imputing this into this equation, yes, or rather I will say work done is equal to minus p, because I'm using what, positive. So minus pv is my work done. So imputing what w is into here, I will have the q plus minus, or will I say d, of minus pv is equal to du. Okay, so this remains minus the pv is equal to what, du. So bringing it to the other side, I have that dq is equal to du plus dpv. So from the knowledge of our ordinary differential equation, we can say that this is what, dq is equal to du plus differentiate p and you leave v, you have, once I differentiate p and leave, you have v dp plus, and differentiate v and leave p, you have p dv. So v dp becomes 0. Why? V dp is equal to 0 because dp, integrating dp from 1 to 2 becomes what, p2 minus p1, which is equal to 0, since p2 is equal to p1, which is a constant for this constant pressure process. So this becomes 0. That means our equation reduces to dq is equal to du plus p dv. Okay, so dq is equal to du plus pv. Okay, so integrating the q and also integrating d plus pv, we have that q is equal to u plus what, pv. Let's integrate this. Okay, let's not jump to this for now. Okay, recall that in the other video we proved that, yes, in the steady state video we proved that h is equal to what, u plus pv. Yes, so if this is it, we'll have that integral of dq will be what, integral of D, this becomes H. So Q is equal to what? Integral from 1 to 2 of the H. So Q heat will now be what? H2 minus H1. This is the heat transfer for the vapor state. Okay, it's the heat transfer for the vapor state. So for a perfect gas, now for a perfect gas, or before we state the perfect gas, so here work done is not zero, because work done, which is dW, which is minus P dV, integral from 1 to 2, becomes what? P what? V1 minus V2. So P is constant here, so this is a value. We have this value. Okay, this is the work done. I have the work done. So imputing into the first law, you can try to find your internal energy. Yes, you can find your internal energy. You can also find your work done. So with that, you can add the heat and work to find your internal energy. So for a perfect gas, for a perfect gas, recall that the ideal gas, we have this what? MRT. Okay, yes. So since W is equal to PV, so it's the same thing as these two. Okay, then you know that we can also say that replacing this with P dV into the first law of thermodynamics, which states that we can say Q plus W. Okay, integrating this, Q plus W is U2 minus U1. Okay, you can still leave this way. You can clean the DW. You can still leave it this way, because this indicates change in Z. Okay, so recall that if W is P V2 minus V1 is equal to P to V2 minus V1, we have that is also equal to MR T2 minus T1. So we have it to be this, because PV is equal to MRT. Okay, having said this, you can impute the value of this and this into the equation. So Q, okay, there is supposed to be a minus here and also a minus here too, a minus here. yes, a minus here, indicating our convention MRT. So imputing this R T2 minus T1, this is equal to, remember, U2 minus U1 is what? CV T2 minus T1. Okay, so our M, remember that, our M, remember it. Okay, we will have that M T2 minus T1 into CV plus R. Okay, but R is equal to CP minus CV. So CP is now equal to R plus CV. So replacing this with what we have here, we have that Q is equal to M T2 minus T1 into CP. That makes more sense because we are dealing with a constant pressure process. This is specific heat at constant pressure. So we have this to be MCP T2 minus T1. So this is for an ideal gas heat transfer for an ideal gas. So having said all this, let's use a question, or let's use some questions to illustrate this wonderful example we have here. So let's use this example to illustrate what we have been saying here. So saturated vapor at 1.5 bar is heated at constant pressure until the temperature reaches 200 degrees Celsius. Okay, in addition to 35 kilojoule per kilogram of heat added as electrical work by passing electrical current through a resistor. Determine the electrical work. So this is an electrical question, a mechanical electrical question. So it's the same thing. The thing is just know the parameters given. Since we know for sure it's a constant pressure process, so you can see that parameters given in the question are a saturated vapor. Saturated vapor means dryness fraction is 1. Dryness fraction is 1. Okay, now the pressure P1 is equal to 1.5 bar. Okay, pressure is equal to 1.5 bar. What else do we have? We have the temperature 250 degrees Celsius. Okay, 200 degrees Celsius. So 200 degrees Celsius. Have it as 200 degrees Celsius. Now the heat, electrical heat, or like call it, okay, the heat added is what? 35 kilojoule per kilogram. So you know that from what we proved in the other page, for steam heat is equal to what? H2 minus H1. So it must be H2 minus H1. So how do we get our enthalpies? H2 minus H1. So from the steam table you look up the pressure 1.5. But before that, remember that this is a constant pressure process. So P1 is equal to P2, which is the same 1.5 bar. Okay, so now from the saturated vapor table, we have that at P. Okay, let me clean this. This looks very dull. Let me clean this. It's very dull. Okay. So I said here P1 is equal to P2, which is equal to 1.5 bar, and also from the saturated vapor table at P1 equal to 1.5 bar. Okay, P1 equal to 1.5 bar. We have that the Vg is 1.159 meter cube per kilogram. Okay, then the Hg is also 2693 kilojoules per kilogram. Okay, now we can go straight to say that H is equal to 1 minus X HF plus X Hg. So since X is equal to 1, this is gone, this becomes 0. So H is S Hg, which is just ordinary Hg that we got before. Now it's 2693 kilojoules per kilogram. Okay, I think that should be H1. So at the same P2, which is the same pressure 1.5 bar, okay, is okay at same pressure 1.5 bar. It was heated to a temperature of, the temperature is 200 degrees C. So this here was supposed to be our temperature T2. Okay, our temperature T2 was supposed to be our temperature T2. So we can write it here. T2 is 200 degrees C. Now you check the temperature at 1.5. Check the steam table. I have my steam table here. I'll open it. So at 1.5 bar, the temperature is saturated temperature is Ts is equal to 111.4 degrees C. So as you can see, it's less than the given temperature, which is 200 degrees. Here you can see T2 is greater than saturated temperature. Hence the steam is superheated. So you go to the superheated steam table. So from the superheated with the steam table, you get that H2 is equal to 2873 kilojoule per kilogram at P equal to 1.5 bar and T equal to 200 degrees C. That's where you get that from. So finally, we can now say that the heat transfer at constant pressure is H2 minus H1. But the question said an electrical work was added by passing an electrical current through the resistor. So it means that Q plus an electrical work will give us H2 minus H1. So finally the electrical work is H2 minus H1 minus the heat. And of course we know the value of the H. The enthalpy to what? 2873 minus 2693 minus 35. So electrical work now will be 180 minus 35. Electrical will be 145 kilojoule per kilogram. So we are done. We have determined the electrical work which stated in the question.
A little liquor and some ladies, yeah. We they turn up on a daily. It's how I walk up, yeah. Soft walk.